I'm John Rice. I am the chair and the CEO of Sigma Labs, Inc. 3D printing is the opposite way to build a part than we grew up thinking about. What does that mean? What happens today when you want to build something like your camera, it's made of metal parts, and people take a block of metal and they put it in a computer-controlled machining, milling machine, and it reduces that piece of metal. It cuts pieces off the metal until it gets to the shape it wants, and then it drills holes in it. And that's called reductive manufacturing, and that's how most things are actually made so far. With 3D or additive manufacturing, it's called additive because you start with just a simple plate, and you take material and melt it into the shape of the part that you want to create. And so what you're really doing, particularly with metal, is sculpting a part into existence in 3 dimensions. It's not like painting, which is 2 dimensions. You're actually making that part grow on the plate as you weld it into place, melting layer by layer, melting metal until you have completed the part. It's being used now in mostly very high technology niches as well as sort of low-tech maintenance niches. And the reasons are that in high technology, there's great sensitivity to product strength compared to product weight. And the ability to make a part that is compliant with your high technology, high quality requirements of tensile strength and other metal behaviors is important. And if you're an aircraft manufacturer and you can cut the weight of that part by 40% or more, that's a big, big win. And so we have seen a number of high-tech manufacturers in the aerospace sector have criteria like, well, we want 40-40 if we're going to make a part with 3D. We want to cut the weight at least 40%, and we want to cut the cost at least 40%. The low end of the market is for parts that need to be replaced because they haven't been made for 40 years, and it's not terribly sensitive to some of the dimensional or quality issues because those parts are from a different generation, but they're simply not available. And so there are machine shops who are making metal parts to replace door handles that were made 60 years ago and things like that. Other areas where this is used are now medicine. Stryker and other companies who make replacement joints are doing a lot of work in this area so that they can specifically, ultimately customize a new joint to your body, your dimensions, and it's a one-off product. They'll make one for you unless you need 2 joints. It is hard to always make the high-quality part no matter what technology you're using. In the case of additive manufacturing, as we switch from making prototypes and exotic new designs and experimenting and move towards trying to do additive manufacturing for production quantities of metal parts, there are some real complexities. We are discovering through technicians and designers that on a plate of maybe 10 or 12 parts, a number of those parts often are not the same with additive. And the theories as to why that is the case vary from gas circulation in the chamber to the fact that perhaps the design requires a different laser power to be used in different segments of the part and so on and so forth. So there's a lot of know-how that is still being gained. And the problem that high-tech people have on getting the quality they want is they need to know that those dimensions are exactly correct, and they need to know that every layer of that part is strong and compliant with the strength and fatigue issues that they are most concerned about. And of course, we have that solution. So the issue is how and when can you ascertain that a part in being manufactured with additive manufacturing or 3D is high quality. And inspecting them after you've made them is not a good way to do it, because you only made 10. And if you cut up 3, you have just destroyed 30% of your outcome. And in the case of additive, as I have just described it to you, you don't know that every part is the same as it was manufactured. Therefore, the post-process idea of cutting 3 up to prove that 7 are good actually has no validity. So the solution to this problem is what Sigma is doing, which is we put probes and sensors into a 3D machine, and we monitor the quality of that part in real time as it is being built. And this permits the operator of the machine and the end user of the product to know that each part that we inspected in real time as it was made is compliant with their standards, or we rejected it. It also changes the mindset of how quality is ascertained. You're no longer doing this on a statistical basis. You're doing it part by part. A part's quality is not assessed relative to another part. The part's quality is assessed on what did we see, and was it properly melted and compliant with the customer's requirements. Sigma came to the 3D manufacturing domain as metallurgists. 3D manufacturing as a quality issue is really about what is the quality and what are the characteristics of the metal you formed as you were making the product. And so Sigma's approach is entirely based on measuring and assessing the manufacture of a part in real time, layer by layer, as that part is made, as the laser goes back and forth and the powder is melted. It simply looks at the melt pool and knows whether or not the temperatures and the size and the behavior of that melting metal is going to result in a part that meets customer specifications. That's a unique idea in the quality world. We have not, in previous quality assessment, really been able to look at a part while it was made with as much precision as we are now doing with Sigma in additive manufacturing. Right now, we are working with a number of customers. We have over a dozen very specific installations of PrintRite 3D, which is our product. It's version, at the moment, it's version 2.0. And it's installed in primarily high-tech people who are looking at assessing this for the future, trying to determine whether this technology will enable them to use 3D manufacturing to make the leap to normal unit volume production. Today they're doing prototypes trying to figure out how to get to volume production. And what they're discovering is that they're not getting the quality numbers of the yield that they expect from 3D to equal their traditional expectations of quality yields. So what Sigma is doing is working with customers to solve that problem. So we are now installed at Pratt & Whitney, Honeywell Aerospace. We have worked with GE. We are with Woodward, we are with Aerodyne, and so it goes. People who are very much at the high end of parts. Well, our dream, as a dream of every technology manufacturer, we want to be the Intel inside. We want every 3D manufacturing machine in metal to have our little logo, Sigma, inside. And the importance of this idea is that it could work. The reason is 3D manufacturing in metal is not going to leap to the hyperspace of volume production unless we change how quality is managed and assured. And Sigma allows real-time quality assurance. And this would allow a number of machines to be in a bank. And even though the machines don't all behave the same way, Sigma would be able to tell you whether each part is compliant and allow the machine operators to change the machine's operations to keep the parts in compliance. What we aspire to do is to make Sigma the digital channel in the marketplace, from design to quality assurance to delivery of a perfectly dimensioned part. All of that occurs in the digital realm. The human doesn't get to touch the part, see the part, use the part until our digital highway has been fully traveled. So we are trying to put together our technologies with other compatible technologies. And there's never any assurance that you can do that. But that's our goal. And as a public company, we're hopeful that we have the capital raising ability and the drive to get this done.